I've got to say, one of my proudest accomplishments in my time at Harvard is convincing David Keith to come join us here on the faculty. David is a very special scholar. David has a background in physics. He did his PhD at MIT in applied physics and experimental physics. And I first met him when he was here at Harvard. When I first moved here in 1997, he was here as a postdoc working with Jim Anderson in atmospheric chemistry. He was now having an experimental physicist working in atmospheric chemistry is a little bit of an unusual move, but David's an unusual guy. He actually has done a variety of different things, essentially working on designing aircraft missions and high altitude missions for various parts of Jim Anderson's program. After he left Harvard, he actually went off to work almost more on the policy realm. So David has always been interested in energy technology and policy. He has cut across both the physics of climate and the solutions to climate change, and spent time at Carnegie Mellon and then up in Calgary. We stole him from the University of Calgary. In some ways, David is most famous for the work that he's going to talk to you about tonight, which is on solar geoengineering. But David also has been deeply involved in recent years in a company outside of Harvard called Carbon Engineering, which is about air capture of CO2. And I think is in many ways leading the field in thinking about how to actually pull CO2 out of the air. What I love about David so much is that he's thinking about every aspect of climate change and will think hard about any way to solve this problem. As you hear David and listen to David about climate change, when you read the media, sometimes they actually get David wrong. They make a caricature of David as some wild advocate for solar geoengineering. And this is an incredibly serious and somber topic. The issues of climate change we're dealing with, the decisions we're making today about our energy systems, and what we will do or won't do in terms of dealing with climate are going to affect the Earth, not just for our children and grandchildren, but for literally thousands of generations. These are serious, serious decisions. And we really don't know what the impacts of climate change are going to be out into the future. I think David's work here at Harvard, and it's not just David, but David has created really a community of scholars, both at Harvard and around the world, focused on this issue, is an incredibly important and responsible thing. Sometimes when you read articles about David, they make it sound like a big advocate for technology. I would urge you to actually, after this lecture, pick up his book. He wrote a beautiful book a few years ago called A Case for Climate Engineering. It is an incredibly thoughtful and responsible book, and what I hope you'll see tonight in his talk is that David is actually as concerned about the misuse of this technology as its use. And I think we need more people in this community thinking like David does, and I hope you enjoy his lecture tonight. So with no more ado, let me introduce David Keith. Thank you.
Thanks very much. Thanks very much. I hope I can live up to half of that. I'm also got to say I'm really thrilled to speak in this series because I've been to some great talks over the years in this series, and I feel it's like kind of intimidating to live up to some of the good talks I've seen here. So maybe as Dan sort of set it up, my goal here is not to convince you that solar geoengineering is something we ought to do or must do. Indeed, I really think the latter is a crazy claim. My goal is to convince you that we ought to take it seriously. We ought to really work much harder to understand what its risks are, understand how we might govern it. We ought to basically bring it into the mainstream of understanding climate science and policy. So first of all, let me start with a very kind of top-level picture about the climate problems. This is the simplest diagram I know of what the climate problem is. And even this has some sort of value judgments in it because on the right, I'm only talking in this picture about the impact on human welfare. And at least for me, I don't just think of the natural world as only mattering because of us. I kind of think it matters on its own. So to me, this is already sweeping some things I care about under the rug. Here's a slightly more complicated version of this diagram. And with this one, we can talk about what are the ways humans intervene to solve this problem. So one way is by decarbonizing the economy, by shifting our economy away from fossil fuels to carbon-free sources, solar power, wind power, nuclear power, what have you, is a way to break the link between emissions and economic growth. In the long run, there is no getting away from the fact that we must do this if we want a stable climate. The best thing you can say about solar geoengineering is that it might be that a combination of emissions cuts and solar geoengineering gets us less risk than solar geoengineering alone, but we don't even know that. What we know for sure is we have to do the emissions cuts. Carbon removal allows us, in principle, to break the link between emissions and concentrations. Concentration is the amount of CO2 in the atmosphere, the thing the climate most immediately feels on a kind of year-to-year basis. Solar geoengineering, at best, partially breaks or weakens the link between concentrations, the amount of greenhouse gases in the atmosphere, and climate change. And then, last of all, adaptation. Adaptation is a way that we can attempt to weaken the impacts of whatever climate changes happen on humans or the natural world. So, for example, we might build dikes to try and protect this campus from flooding. So my focus today is on solar geoengineering, but make no mistake, the most important topic is decarbonization. That's the one that we cannot get away from doing. So this topic is controversial. I think it's justifiably and sensibly controversial. There's no running away from that controversy. I think that's a healthy part of it. And maybe to open it up, here is some examples of some of the things people say about this technology over the years. And some of these are really sort of startling quotes. And the one that's most surprising here, that gets at actually the deepest fear, is this quote that says, "It's batshit crazy, a powder keg for priming the global explosion of unintended consequences." It's not that statement, which is a perfectly reasonable statement, actually. It's who's making it. This is from a climate denialist, climate skeptic website. And so what's really interesting is a lot of us guessed, and I think one of the big fears about, justifiable fears about this technology, is that it will serve as an excuse for people who want to avoid emissions cuts. And so it's quite odd that this website that seems to be mostly trying to make excuses to avoid emissions cuts is making this claim. So what is the technology? So the simplest way to say it is the idea that humans might deliberately alter the radiative balance of the Earth so as to try and push the Earth closer to its radiative equilibrium in the opposite way from greenhouse gases, which are trying to push it away from radiative equilibrium. So in simple terms, it could restore temperature, but many other things as well. And it's an attempt to do that deliberately. There are already many ways that humans do it unintentionally. So key to geoengineering in defining it is the idea that it's deliberate, that it's a human action to alter the radiative balance of the Earth, and it's attempting to do it at some scale that's global. So what are the risks? I'm going to first give you just a little scattershot, a picture of a whole bunch of risks of this technology in a mess. Towards the end of the talk, I'll try and organize these into some categories. But before I do that, I'm going to try and give you a simple story about what the technology is in a particular kind of it, what its direct risks might be, what it might actually do to reduce climate changes we care about. Then I'll say a little bit about what the uncertainties are, how experiments might address those uncertainties. Then I'll tell you about what the sequence of these things might be through time. So in some kind of optimal or wise climate policy, how we might link up emissions cuts, carbon removal, and solar geoengineering through time. And then I'll come back to risks again in detail at the end of the talk. So this is a messy picture. I'll come back to it a second time. That gives you a sense of all the different, or most of the different technologies that people are talking about as methods that could be used to do solar geoengineering. And for right now, I'm going to focus only on that first one, which is the idea of putting sulfuric acid, or sulfate aerosols, into the stratosphere about 20 kilometers over our head. That's the thing that we are most certain could actually be used with existing technology. And this is really not an overclaim. If one wanted to, you could stop the planet warming over, say, the next century or half century using this technology at ridiculously low cost. That does not mean it's a good idea. It does not mean the risks are low. it really means that cost isn't the issue, and that global temperature, while it's this proxy we all think about, is just a proxy for all the local climate changes we actually care about. And you should ask yourself how much these technologies can actually help with many of the local climate changes we care about. So I'm going to sort of set up a benchmark idea of how this might be used. And the benchmark idea, first of all, is a kind of techie number up the top. The benchmark idea is that we might use it to make 2 watts per square meter of radiative forcing. Radiative forcing is the way the climate science world talks about how much humanity is pushing the world. So 2 times CO2 makes roughly 4 watts per square meter of radiative forcing. So 2 watts per square meter of radiative forcing, this benchmark, is enough to offset roughly half of the effect of doubled CO2. And scenarios for late this century run anyway from a few watts per square meter up to sort of 8 to 10 watts per square meter. So this 2 is a middling benchmark, and I'll tell you a little bit about how you would do it. So to do that, you need to put something like 1.5 million tons of sulfur. That's of elemental sulfur. Then in the stratosphere, you turn it into SO2 and then to H2SO4. You need to put it into the stratosphere. And right away, you should think, my God, you're putting sulfuric acid up in the atmosphere deliberately? And that clearly will make some risks. But you can see on that slide 2 useful comparisons that give you empirical sense, because I don't just trust what theory says, I trust empirical experience. Give you an empirical comparison that tells you something about what the risks might be. So one of them is that the eruption of Mount Pinatubo in '91 put about 8 million tons of sulfur in a single year. So we're talking about much less than that. And annually right now, we put about 50 million, I think it's a little lower right now, million tons into the atmosphere as pollution from fossil fuel combustion, and it kills several million of us every year. So this is serious business. You would put it into the atmosphere, or you could put it in the atmosphere, with a fleet of roughly 100 aircraft. These would not be existing aircraft, these would be new build aircraft, but they're new build aircraft that are put together essentially with existing components out of existing aircraft building knowledge. So this is absolutely not unobtainium. It's something that many different aircraft developers around the world could do if you paid them the money to do it, with very little technical risk that it fundamentally could be done. And this would take something like 120,000 flights a year and have a kind of direct cost of $5 billion. So again, those numbers, think 120,000 flights a year, it seems like a big number, but as a reference, right now we're doing almost 40 million flights a year of conventional, of commercial transport aircraft. So 120,000 is not, I think, in some respects, a very big number, and 5 trillion is pretty small compared to GDP of 100 trillion-ish. Or to climate risks. So you should wonder, how on earth such a small amount of kind of money and stuff and material can have that big an impact on climate? So before we get into all the risks and the politics, I just want you to think about the sort of scientific amazement. Why is it that putting that, I mean, 1.5 million tons a year seems like a lot, but that's a tiny amount of material compared to other things that humans do. And it's a tiny amount of money and effort compared to other things humans do, and yet it has this giant impact. Why? The answer is that a few grams of sulfur in the stratosphere offsets just the radiative forcing, not the whole climate impact, we'll get into that, but just the raw radiative forcing of about a ton of CO2 in the lower atmosphere. So that's a leverage of almost 1 million to 1. How is that? What's the physics that make that happen? Well, there's a really beautiful kind of example of that physics that you've all seen all the time. Why do clouds appear out of an otherwise cloudless sky? So here's a picture from, my wife and I live both here in Cambridge, but also in Western Canada, in Canmore, Alberta. And this is a picture from our house in Canmore, Alberta that my wife took. And indeed, we'll be, hopefully in 3 days, out ice climbing in those mountains. And I'm sorry, it's a low resolution picture, but you can see lenticular clouds. These are clouds that are formed as air flows up and down over a mountain. Hopefully many of you have seen these lenticular clouds. And so you should wonder about this. The amount of water vapor in the cloud, the amount of water vapor here, is just the same as the amount of water vapor in the completely clear sky upstream of the cloud or downstream of the cloud. So how the heck does this water vapor get to be so bright? And the answer is because water as vapor, as little molecules of water, don't scatter light very well. And water is a big lump of water. If I took all the water in that cloud and I made it into a big block of water, kind of little aquarium-sized thing of water, it would just be a little aquarium of water. It wouldn't reflect very much light. It would fall. It wouldn't be a light reflector. It's a light reflector because it's organized into little drops that are about the size of a wavelength of light. That's the magic of the way aerosols have such strong radiative effect. They're basically a way to make mirrors that are of order a micron thick. That's a really kind of amazing piece of scattering physics that shows you the reason aerosols are so important in the Earth's climate for this topic, but for many others. That's the underlying reason why aerosols are so important, and also gives you a sense of why climate modeling is so hard. Because little changes in the way this works make huge changes in how white the cloud is, which make big changes in the climate. So it gives you some sense of why clouds are hard to model in the climate system. So where would you put this stuff? The stratosphere is around here, maybe about 10 kilometers or 30,000 feet over our heads. In the tropics, more like 18 or so kilometers over our heads. So if you've flown an aircraft from here to Europe, you'll fly in the stratosphere, but in the tropics you won't. Regular aircraft fly at about 10-kilometer altitude, sort of 30, 40,000 feet. That's not high enough to get into the tropics, into the stratosphere in the tropics, where it's almost twice that high. So where we would inject material is mostly in the tropical stratosphere, and it turns out that there's a circulation in the stratosphere where air flows roughly up in the tropics and then down at the poles. And if you adjust the way material is injected roughly in the tropics, you can, just by injecting the tropics and just by injecting at one longitude. So you could do this all in principle from a single airfield located somewhere in the tropics. You could get a very even global coverage, even north to south and even pole to pole of these aerosols. And we've done a fair amount of modeling to show that with feedback and control, you could achieve a reasonably even coverage. And the rest of what I'll say is about what the effects of such an even coverage might be. But again, before I tell you what the climate benefits might be, I want to say more about risks. So there's lots of risks we don't know about. That's the whole problem. It's like we look under the light post at what we do know. But here's a little bit about some of the risks that we have at least begun to quantify in a serious way. So if you're going to put aerosols in the atmosphere, you've got to worry right away about what are the health impacts, because we know that aerosols have big health impacts, and Harvard School of Public Health has been probably a global leader in helping us understand what those are. So actually, first of all, I got ozone. So putting sulfur in the stratosphere can damage the ozone layer. It's not exactly that the sulfur does it on its own. It's that it amplifies the effect of the chlorine and nitrous oxide that we put there for other reasons. The chlorine from chlorofluorocarbons, the things we banned under the Montreal Protocol, and the nitrogen oxides from combustion all around the world. So if we do this in this kind of benchmark scenario, we would reduce the amount of ozone in the stratosphere by something of order 8 to 10% round numbers. And that would cause excess, the direct impact of that would be to cause excess mortalities of order 6,000. This is very unscientific. I've led these things with no uncertainties because the uncertainty bars are hard to read and confusing. But you should think of all these mortality numbers as being uncertain by factors of like 50% or even more. But this at least gives you a kind of sense of the numbers. But the net change of mortality is actually a big negative from ozone, from total ozone. And that's actually because when you cool the climate with this effect, you make other changes in atmospheric chemistry in the surface. And those turn out to mean that surface ozone, the kind of ozone that's bad to breathe, gets lower in an atmospheric chemistry model, and we're pretty sure in the real world. So this direct effect is the one that you most immediately think about. Then you can look again at particulate matter pollution. So we're putting particulate matter in the stratosphere. You've got to worry about it coming back down and killing people, making them sick in the lower atmosphere. And the direct number is about 11,000 people a year, which is certainly nothing that you should ignore. You're talking here about making decisions that would have that kind of impact on people's lives. Of course, this isn't a case where you identify who died. It's about changing the number of people who die from a whole bunch of diseases that are linked to fine air pollutants. But that number turns out to be really small compared to the net change. And the net change are all sorts of changes due to the fact that we partially reduce climate change. So it turns out that for a given human emissions of air pollutants, how much of those human emissions turn into particles that cause health impacts depends on the climate, depends on the amount of rainfall, depends on temperature. And those climate changes actually end up making significant extra mortality, but I count that kind of morally differently, because the whole point of this is we'd like to have less climate change. So current global mortality, to give you a sense from outdoor air pollution, is of order 4 million. So all these numbers are really quite small compared to that. And then the real comparison that you want to make is, of course, compared to the benefits of this in reducing damages from climate change, and we'll get to that. But this gives you some rough quantification of what some of the direct environmental harms we know about are. I'm happy to answer more later. We're talking about something that would reduce sunlight at the ground level of order 1%. So would this reduce climate risks? Which one, how much? It'll definitely reduce global average temperature, but what does it do for the things we care about? So there's actually now quite a lot of evidence. There's been an order of 1,000 papers published on this topic. In some sense, there's been a kind of research taboo. We'll get to that. But there's some real evidence. And I'll show you results from a single paper that we did in collaboration with Kerry Emanuel at MIT and with a research group at Geophysical Fluid Dynamics Lab, the kind of first original climate modeling lab. But it turns out that I happen to like that because it's my paper, but we've shown that these results are replicated in a whole suite of 12 climate models getting basically the same answers as I will show you. And I would say the evidence is sort of the following. There's quite strong evidence that solar geoengineering could reduce the changes in water availability that are caused by climate change. So one of the central things to know about human-induced, CO2-induced climate change is that it tends to make the wet regions wetter and the dry regions drier. Many of you know sort of anything about the climate problem know that. And so the obvious question is, what happens when you do solar geoengineering? Does it tend to make that worse, better? What happens? And the answer from really all climate models is it tends to reverse it. That is, it tends to make the regions that got wet a little bit drier, bringing them back towards the pre-industrial, and the regions that got dry a little bit wetter, bringing them back towards the pre-industrial. I'll show you some data about that in a second. And does that not global average, but on a regional basis. It reduces, and very strongly, regional changes in extreme precipitation. These are the things that drive big floods, for example. Likewise, for tropical cyclones, although it's harder for us to say anything meaningful about regional impacts of cyclones because we don't trust the models in terms of regional cyclone activity very well. But the drop in cyclones is pretty dramatic, and those have big human impacts. So this effect, which would drop the overall climate change from doubled CO2 in half, would drop the tropical cyclone activity in terms of sort of energy of cyclones almost back to pre-industrial. So you get a really strong effect in reducing tropical cyclones. Reduces extreme temperatures. So let me tell you a little bit about where these results come from that I'm claiming. So I mentioned they come from this model at the Geophysical Fluid Dynamics Lab, and this shows you a little simulation of the model making hurricanes. And I started working on climate as a postdoc at National Center for Atmospheric Research in the early 90s, and at that point, there were no models that just autonomously generated hurricanes out of model code. We had little Fortran subroutines that kind of pretended to be hurricanes. And it's really, to me, quite amazing and quite exciting that climate models now will replicate what hurricanes look like in the current climate with amazing fidelity directly out of the model physics. That's really quite an exciting thing without a lot of kind of hand tuning. And so they get the distribution of hurricanes. This is the plot on the left, the distribution with respect to how many big ones you have versus small ones. And I'm not showing it, but they get the distribution in season and area really remarkably well, which to me says something really strong about the idea that these models have something real to say about the climate as it works and about especially how precipitation and precipitation extreme work. So that's the model that we used and collaborated with. And we ran a model experiment in this one where we just turned down the sun, literally adjusting one number in this monster climate model. Obviously, real geoengineering doesn't turn down the sun, although there are actually ways we could approximate that. But it turns out, as I said, that you can replicate this in models that do this with sulfur. So this shows you the change in surface air temperature over the whole land surface, where the red is what happens under 2 times CO2, and the blue is what happens under 2 times CO2 and this 2 watts per square meter of solar geoengineering radiative forcing. So the red has a higher median, and there's the extremes in the red go right up to 4.5 degrees centigrade, these very high temperatures that a lot of us worry about. And in the blue, you'll see the extremes are reduced dramatically. So this gives you a sense that this isn't just working on the means, but it's working on the extremes. That's for temperature. This is for extreme air temperature. The hottest is the change in extreme air temperature, the hottest hour of the year. This is for the wettest 5 days of the year, and this is for water availability. So for some of these things that are the most important, what are called the hazards, the physical hazards that drive the human and environmental risk. For some of these, which are not randomly chosen, but some of the most important drivers of physical hazards, you can see that solar geoengineering has really done, in this model, a pretty dramatic job in reducing the distribution of these changes. But this could be true, and it could still be true that there are some regions that are made worse off. You can't tell that from this plot. So it could be, for example, here, that there's some region that was here, and moved to there. So some region, even though on average things have got better, there's some region where say, extreme temperatures got bad under 2 times CO2, and they got worse under solar geoengineering. And one of the big questions is how unequal this is. How much it helps some people and hurts others. And I and many other people had written a lot in the public policy of this topic, arguing that a big problem with solar geoengineering is that it was inherently very unequal, that some areas would benefit and some areas would lose. And so one of the big things we did in this study was to look very carefully, region by region, at what would happen. So we used some standard regions that are outlined there, that are standard in the way the Intergovernmental Panel on Climate Change has looked at extreme weather events. And for each of those regions and for each of the variables, those 4 variables, temperature, water availability, this is precip minus evaporation, extreme temperature, and extreme precip, for each of those, we divided the world. We analyzed whether statistically significantly things were made less bad or less climate change, or whether things were exacerbated, that is more climate change, which is in general worse, or whether you couldn't tell, because in lots of regions you are statistically unable to assign them to one or the other. So I think we did a slightly carefuler job really thinking through the statistics in what I think is a policy relevant way, because what people want to know, what local decision makers want to know, there's no one decision maker for the world, is what's the likelihood this will make my region better or worse off? So then things are color coded, so the bright red symbols are the ones where one of the variables were statistically significantly exacerbated, that is made worse off. And the big punchline of this is there are no red symbols. So no single red symbols, let alone having several different red symbols in one place. So this may or may not be true. And I think one of the biggest questions for solar geoengineering is wondering whether these results are too good, and if so, why? Is there some reason that models are exaggerating the way solar geoengineering works? I can tell you, this group had never run a solar geoengineering experiment before. They did not tweak the model to make it look good. But nevertheless, you have to worry about that. But this is extraordinary. If there is a single reason to take these technologies seriously, I think this is it. That is a sense that they really might be used to reduce some of the climate hazards we care about the most on a region by region basis without making any significant large region worse off. That's a very strong claim. And I don't think we know it for sure. But the fact that it might be true is, I think, the reason to think hard about these things. It reduces sea level rise. That's exactly how much, and whether it could slow down or stop a really dramatic sea level rise is something we don't know. But in some sense, some part of that is an easy one. Surprising, but true, it reduces the growth in carbon in the atmosphere over the century. That's quite surprising, because many people think that solar geoengineering actually makes ocean acidification worse. And there's a political way in which that might be true. But let me give you the technical story first. So in some sense, it's not complicated. Carbon emissions put more carbon in the atmosphere. More carbon in the atmosphere makes it warmer. Warmer means that that the ocean absorbs less carbon, and that things like, say, permafrost ecosystems release more carbon. These things are called carbon cycle feedbacks. There's nothing that's new about this. This is stuff we've known. We argue a lot. The climate community has big uncertainties about exactly how big these feedbacks are, but the general direction of these feedbacks is well understood and been studied for decades. So if you look at 2 worlds, both of which have the same human emissions of CO2, but in one world you do some solar geoengineering, so there's less temperature change, but the same human emissions of CO2. In the world with less temperature change, these carbon cycle feedbacks are weaker. And that means that even though you've put the same amount of CO2 into the atmosphere, at the end of the century, there's a little less there, like 10% less there. This does not get you out of the fact that the fundamental driver of CO2 in the atmosphere is human emissions, and if you want to deal with that, you have to deal with human emissions. But it's not nothing. This is like eliminating US emissions over the century. Reduces global average temperatures. That's the obvious one that we know. So why do we believe this? I showed you some results from one particular paper we've done, but there's now been efforts to study this with an ensemble of 12 different models, and really a lot of investigators have looked at it. And maybe most importantly, it's now been 19 years since Ken Caldera first ran a climate model to explore the effects of solar geoengineering. And actually he, like many others in the scientific community, had a bias, I think a really healthy bias, to be very worried about tech fixes like this. And so I think we've had a bias to look for problems, to try and find reasons why this isn't true. And so after 19 years of modeling, after lots of papers published, I think it's hard to find a paper that contradicts, a single paper that contradicts any of this. That is a single paper that looks at a case of spatially uniform, this kind of moderate solar geoengineering that doesn't reproduce answers like that. So that's to me the reason to think about it seriously. So, by the way, these background pictures are all personal. This is from a camping trip in the high Arctic. So now I want to get you to think a little bit about uncertainties. So far I've been talking about how much we know, what I think will happen, but uncertainties here are deep. And most of them are deep because there's only been a small group of people that have looked at this seriously. There has been, and I think for the fundamental reason of concern that work on solar geoengineering would be exploited as a way to fight against emissions cuts, there's been virtually no research on this topic. So to give you a sense, the actual ideas I'm talking about are old. The first major climate reports, like the first report that went to a US president, President Johnson in 1965, talked about climate roughly with a lot of the same science we know now. First wet climate model, first measurements of CO2 in the atmosphere. And they talked about what we would now call solar geoengineering. They didn't call it that name then. The big reports out of MIT around 1970, the National Academy report on energy and climate in 1977, the report in 82 or 83, all these reports dealt with this topic. But then, as climate became more part of a political fight, I think it's fair to say that many people in the kind of climate science and policy community felt that we just should not deal with this. And so for years, there was virtually zero research. That taboo was, I think, began to get broken about a little over a decade ago when Paul Crutzen had won a Nobel Prize for atmospheric chemistry, understanding the ozone layer, and really wrote a short article saying stuff that had been said before. But I think because he wrote it, it had an impact in getting a little more research. But even now, as much as we can estimate it, the total amount of research globally directly funded on this topic is of order 10, maybe $15 million a year. And to give you a sense, US budget for climate science, including the satellites and so on, is about 2.7 billion. I don't know the global, but I'm going to guess it's close to 10. So it's really very, very small. And that means that there's a small group of us who've all been talking about this, and maybe we're a little inbred, and maybe it's a bit of groupthink. So I don't trust any of these results enough to make decisions with. What I trust them is to say that there's something interesting here, and that we ought to have a much more serious research effort to understand it better, and especially a research effort that really thinks hard about what the holes are, about why things might not work. So what kind of research do we need to do? There's all sorts of ways in which we need to look at places where we know models are deficient in ways that matter for solar geoengineering and fix them. So there's a whole list of specific ways we need to know how to do that. But models are just built on previous experiments. They didn't come from just somebody dreaming them up. They came from centuries of scientific measurements in the outside world. And I think you can only really understand, and especially you can only understand some of the complexity of the outside world, which is always more complex than we think and always surprises us if you actually go do experiments. So I've been advocating for, and now colleagues at Harvard are really thinking about the kinds of experiments we could do to reduce our uncertainty about these technologies. Not experiments that manipulate the world or that test solar geoengineering, but experiments that measure specific things that could tell us more about how solar geoengineering might work, what its risks might be, or what its efficacy might be. So one sort of experiments are, oops, I forgot I had that slide. I'll go first the experiments and then come back. One set of experiments are just experiments in the lab. These are experiments that are things that have been done in atmospheric chemistry for a long time. This experiment that my PhD student Jen Dye has just finished up. And the experiment measures reaction rates at temperatures that are relevant to the stratosphere. And with stratospheric gases, we use chlorine nitrate, for example, which is not an easy gas to make. And we react it with some chemicals to test the reaction rates. And these are reaction rates that we have in the model, but we don't really believe them because the chemicals we're using, calcium carbonate, people haven't cared about it in the stratosphere very much before, and we do for reasons I'll get back to in a second. Sorry, I'm out of order. And so that's an example of a simple lab experiment, but a simple lab experiment that we need because only by doing those experiments can we improve these coefficients in the models that in turn improve the fidelity with which models can say what might actually happen in the real world if we did this. And sorry, I'll go back and forth here. Let me go back to this list of different kinds of solar geoengineering that might be possible. So I talked first just about this idea of putting sulfuric acid in the stratosphere. It's the oldest idea. This idea goes back to the late 1960s. And in many ways, it mimics something we know nature does. Big volcanoes put SO2 in the stratosphere. The SO2 oxidizes to sulfuric acid aerosols, and they cool the climate, sometimes dramatically. So we know something about that. And there's been decades of studying, because of volcanoes, the sulfur cycle in the stratosphere. So we know a fair amount about both from a big range of observations. Our group and some others have started to think about other aerosols that we could put in the stratosphere. So for example, we're kind of excited about the idea that calcium carbonate, limestone, might work better as an aerosol in the stratosphere than sulfates. And there are a couple of reasons. One reason is that it actually, instead of damaging ozone, it tends to help the ozone layer a little bit, because sort of high school chemistry, a base like that reacts with some of the acids in the stratosphere, the HCl, hydrochloric acid that we put there from chlorofluorocarbons. It reacts with those and tends to take them out of the stratosphere. And so it turns out that it will, as well as tending to restore the radiative balance of the Earth, it'll tend to restore the ozone layer a little bit. That was kind of the thing that got people's attention about this calcium carbonate idea. But actually, I think the important thing is that calcium carbonate looks like it might have better radiative properties than SO2. SO2 absorbs sunlight a little bit, and that means that as well as reflecting it, it absorbs some and it heats the lower stratosphere. And that causes a bunch of problems. And calcium carbonate does much, much less of that absorption. So that's one of the reasons we're interested. I wouldn't in any way say we know that it's a good thing. There's a bunch of other solids that we're looking at. But so the reason that we're doing experiments like that experiment of Jen's is to try and understand quantitatively what calcium carbonate might do under stratospheric conditions. So we're also thinking about, sorry, I'm going back and forth. I can tell I'm out of order. I haven't given my talk quite this order before. Let me quickly go through the whole list, actually. So those are things we do in the stratosphere. Then there's two different ideas about how clouds might be modified. And they actually go opposite directions, which is confusing. So one idea is about low marine clouds, the kind of clouds you see off the coast of Vancouver or Seattle, marine stratus clouds. And the idea is that you could inject sea salt aerosols, tiny sea salt particles made by just evaporating seawater, into those clouds, and it would make the clouds a little bit whiter. Basically by meaning that the same amount of water in the cloud gets divided into more little droplets, and so it makes them even more efficient scatterers, back to my cloud picture I showed you earlier. So that idea is called marine cloud brightening. The other idea is that cirrus clouds, these high wispy clouds, the cirrus clouds actually tend to warm the climate because they act as infrared heat trappers even more than they act as reflectors. And so in some cases, you could add a little dust nuclei to cirrus clouds, and you tend to thin them out, make them fall a little bit faster. And that's called cirrus cloud thinning. And it might actually be very effective in restoring Arctic temperatures. Both of these techniques, I would say, we have much less certainty about whether they even work at all. So if you tell somebody an exact sequence of how you would put aerosols into these marine boundary layer clouds, at this point, we don't even know for sure what the sign of the response is in some cases. That is, we could make it a little brighter or a little darker. And for cirrus clouds, there are really big uncertainties. But those uncertainties, from my point of view, are a reason that we should go study it. Because if we go study it for geoengineering, one thing we're going to learn is more about how these clouds work in the climate system that help improve our models. So I think there's very strong arguments for studying these two seriously. Finally, it's possible in principle to build structures out in outer space in between the Earth and the sun. People have talked about this for decades. In the last 10 years, there hasn't been much attention to it. We're actually organizing a big meeting with a bunch of really kind of top people in the space technology and sort of big thinkers about space are coming here in 3 weeks to talk again about these technologies. We'll see how serious it is. My view is that if we're talking about doing this in the next 3 decades, then we're certainly not going to do some space-based thing. We're going to do it with aerosols if it gets done. But if you're talking about doing it sometime in the latter half of this century, it might well be that a space-based method would really have substantial advantages and would have costs that were reasonable. So that's some overview of the kinds of technologies. This is that experiment again. And this is our outdoor experiment. So this is an experiment that Frank Koich and I and a bunch of others are involved in. Frank is now leading to fly a balloon and make a measurement in the stratosphere. Again, first of all, with calcium carbonate to understand how it interacts with itself and how it interacts with background chemistry of the stratosphere and how it mixes. And this experiment, by being an outdoor experiment, has attracted a fair amount of attention and controversy. We've tried to set up there's a formal advisory board advising the provost for research at Harvard who will make the final decisions about what happens. But I should say that this is not a test of whether geoengineering works or not. This will alter the climate. We're talking about something that puts of order a kilogram of materials into the stratosphere. So it's tiny compared to the environmental impacts of even an airplane flight, which can put sort of kilograms of materials every minute that it flies, kilograms of sulfur every minute that it flies. But it is a way to do controlled experiments that allow us to test specific things in the stratosphere that will help improve our models. Things that we simply have question marks about in the models now. So that's one example of many experiments I think we would need to do if we're going to improve the science of solar geoengineering. So now back to this image and back to the question of what is the sequence over time? How do these things fit together? So first, I'm going to tell you a little more about carbon removal, which I haven't said anything about. I'm not going to say anything about cutting emissions. We have to do it. There's all sorts of ways to do it, but I won't get into the details. But carbon removal is a little less familiar. Here's a big list of ways people talk about removing carbon from the atmosphere. And that list just looks like a mess. And it hides the fact that there's two really different categories in there that I think just shouldn't go with the same name. So one category are things that and this doesn't things that remove carbon and put it back in the geosphere, put it away for timescales of millions or tens of millions of years. So I think it is fair to call these things truly negative emissions. So if we burn coal or oil or gas and we put a ton of carbon in the atmosphere, these things could actually negate that by putting it back essentially in the geosphere in places like where the coal and oil and gas came from. There are plenty of risks, there's uncertainty, there's costs, but there's certainty that you could really put it back where it will stay isolated for a long time. So in thinking about that, what climate change is caused by ultimately is by us burning fossil fuels, moving carbon from the geosphere to the active biosphere, where then carbon can equilibrate naturally between the atmosphere and the land biosphere, as plants grow and plants decay and with the ocean. This is mostly a natural process, and it mostly happens on pretty short timescales. So all of these things are really about shifting between these three reservoirs. And I think you shouldn't call any of these things negative emissions, because they don't negate the fundamental long-term risk of burning a ton of carbon. That's not to say they're not useful. So I think you might call them carbon banking, or maybe you call them carbon reservoir management, which is a sort of geeky, or you call them delayed emissions, because I think that's really what they are. So if you emit a ton of carbon now and then you plant a tree, that tree can't be permanent. It depends on future climate change. It depends on choices about forest management. So that doesn't negate the long-term environmental consequence of burning a ton of carbon, but it shifts that consequence out in time, and that might be actually really beneficial. So this is not me saying that this stuff is good and this stuff is bad. It's me saying these are different, and we should not count them with the same word. And in particular, we should not fall into the moral hazard of thinking that if we burn a ton of carbon and then buy one of these carbon offsets, that we have somehow eliminated the environmental damage from that ton of carbon. That, to me, is the same as what the Catholic Church used to do in selling indulgences. So how do these things fit together over time? First of all, if we just burn fossil fuels forever, even at a constant rate, so not with a rising rate, but if we kept the rate of fossil fuel combustion constant, then the climate risk grows without bound. We won't do that. I am absolutely confident that we will bring emissions to zero. It's a big political fight. It's technically possible. We will get there. We will get to a day where we have a big global celebration of net zero day, where there's zero net emissions of CO2. And on that day, we have not solved the climate problem. We've just stopped it getting worse. Because climate is a stock and flow problem. Climate depends on the cumulative emissions of CO2. So when you bring emissions to zero, you don't make the problem go away. You just stop the problem incrementally getting worse. It gets better very, very slowly, but not on human timescales. It's one of the most important things to know about climate. And it's one of the central reasons that it is not, I think, sufficient to say that the only thing we should think about is cutting emissions. We have to cut emissions, but cutting emissions does not make this problem go away. So it is possible to do carbon removal, to gradually take carbon out of the atmosphere. And no question some of these methods could work, some of these negative emissions technologies, but I think they're all inherently expensive and slow. In the near term, it's for sure easier to spend the money to avoid emitting a ton of carbon than to emit a ton of carbon and recapture it. There's a lot of hype and excitement about carbon removal right now, and I founded this company that does direct air capture. I'm very excited about it, and we're sort of benefiting from this excitement. But I think the idea that we're going to use really large-scale carbon removal very soon because somehow we can't get it together to cut emissions, that idea makes no sense. Because the reason we can't get it together to cut emissions is a political difficulty of agreeing to spend the money to cut emissions. And it's going to cost more or less the same money or more to do negative emissions. So there's no reason to think that won't be politically harder. So I think negative emissions are useful principally in the near term for making carbon-free fuels, but in the long term, once we've driven emissions down towards zero. So how does solar geoengineering fit in? I think solar geoengineering most sensibly fits in to carve the top off that risk profile. That's the key thing. And that means it needs to grow, start relatively soon, grow slowly, and then fade away slowly. And that growing slowly is key because it means you don't start this all at once. So some people think of solar geoengineering as something we do in an emergency where you hit a big red button and turn it on. I think that would almost never make sense because you can't learn your way up. In a scheme like this, you can start slowly, adding a little bit more of whatever it is, watching very carefully for side effects, maybe figuring out something else you want to add, and learn your way up in a slow way. I think if we ever do it, that's the way that makes sense. So how do these fit together over time? Emissions cuts start at the moment where the business as usual, do-nothing profile diverges from the real world. Maybe you could call that kind of now. So we are beginning to get beyond talking cutting emissions. We spend $300 billion a year globally now. That's the Bloomberg New Energy Finance number on clean energy. That sounds great, but it's probably 3 or maybe 6 times less than we should be spending. And it's also about the same as the number was a decade ago, which is pretty depressing. But it still is progress. Then there's that day I said, the global celebration day of zero net emissions. This graph doesn't say when it is. I sure hope it's in my lifetime, and I think that is achievable. But it's not going to be in 15 or 20 years. Then there's solar geoengineering. This is still without any time axes. And you can see that solar geoengineering, by definition, in this scheme where it's going to cut that top off, it has to start a long time before that day of zero net emissions, that day which is more or less the peak climate risk. So then when's large-scale carbon removal? To be clear, some carbon removal is already happening, and that's great. I'm very excited about carbon removal. But I don't think it makes sense to do really large-scale carbon removal until we've driven emissions down to maybe 1/3 of their current level, until we're basically getting to the emissions that are really hard to cut. And that day will come, but I don't think that day is quite yet. So this was all done with no math. It's all just the high-level picture. I will quickly get a little more mathy and show you results from an economic model, and then I'll go back to a really simple picture and to risks, and then I'll wrap up. So this is from an economic model, and it's from the model that some of you may know, an economist called William Nordhaus won the Nobel Prize recently for environmental economics. And the principal thing he did was build this model called DICE, this simple integrated assessment model that has been the most important model in helping people think in economic terms about how to manage the climate problem. And this poses the climate problem as a kind of competition between the costs of cutting emissions, money we spend now, and the long-run benefits of cutting emissions, which are mostly in the future. And the results of this model entirely depend on the assumptions. What I like about this model is it's really simple, and you can see what the assumptions are. So in a model like this, you have to have some estimate of climate damages. You have to have some estimate of the cost of cutting emissions and baseline. So this shows you the absolutely standard Nordhaus model. This is run out, in this case, to the year 2250. This is from my postdoc, Maria Belaya, who I think is in the audience somewhere. And this shows you what his baselines are, and this shows you what the economic damages are and what the temperature is. Here's something that may be surprising and disappointing. There's been a lot of public argument with Nordhaus. So Nordhaus's answer for what his economic optimum is, and in some sense what he recommends is the right utilitarian optimum for humanity, his answer is we stop temperatures rising at about 4 degrees C. Most people don't agree with that. Most climate scientists don't agree with it. I think most activists don't agree with it. I don't agree with it. But I don't think it's a foolish answer. Nordhaus is a very serious, thoughtful person, and he has done this very carefully, listening to criticism and adjusting the model over the years. And that's what an economic model that tries to turn everything into utilitarian or money terms, that's the kind of answer it gets. You can get different answers in different ways. You can get different answers out of this model by tuning it, but that's what's in it. So far, I haven't told you anything that's not standard to this model. Now, myself and Maria and some collaborators, we wanted to put solar geoengineering to this model. And the big question is, it's easy to put geoengineering as a thing that reduces climate change. The big question is what we do for the damages of geoengineering. Because if we just put geoengineering in as a way to stop it warming, because this model only knows about temperature in one dimension, and we just put that ridiculously small cost I had of $5 billion, then the model will just do geoengineering and nothing else. And we're very convinced that's not the right answer. So what we did is what we think is a very conservative assumption. What we did is we assumed that the damages of geoengineering, that is the harms it does, monetized in whatever combinations of bad things it does, the damages it does, if you use it enough to compensate the full effect of 2 times CO2, the damages are just as bad as the damages from 2 times CO2. I'm really pretty confident that's a very conservative assumption. That is that the real damages seem to be a lot less than that, but we wanted to be conservative and we wanted a simple assumption, so that's what we used. So this gives you the answer if we do carbon removal and solar geoengineering in this model. It shows you what the model does. So this again shows you the baseline. And so in this model, temperatures go up, they peak around 2150, and then they gradually come back down. That coming back down is carbon removal working slowly because it's expensive, but gradually pulling concentrations back down. And this shows you the way solar geoengineering grows and then goes down. So I showed you this thing, the thing I showed you before has become called the Napkin Diagram. It grew out of some work at the UK Royal Society a decade and a half ago. And I think this is the first model that's kind of quantitatively made a picture that's like the napkin diagram. So this shows you some pictures. Then it gives you some idea of the numbers. If you want to think about climate in purely economic terms, it says that solar geoengineering could save something like $10 trillion a year by the end of the century by reducing damages from like 2.7 to 1.5 or so % of GDP. That's not counting this quadratic damage. So that's a useful way to think about it, but it's pretty complicated. Let me try and distill all the stuff I just said into something that I think really should surprise most people who think about climate policy. So if you asked maybe all of you, or most of you anyway, what your preference order was, my guess is most people would say first preference is emissions cuts, then maybe you'll think about carbon removal, and then distant third preference, maybe even don't want to talk about it, solar geoengineering. So that's most people's preference order. And most people, I think, assume that the time order should be sort of like that we first do emissions cuts, and if they fail, then we do carbon removal, and if that fails, we do solar geoengineering. It's common to hear versions of that statement. I cannot figure it out. For one thing, what does it mean that emissions cuts fail? There's no technical doubt we can cut emissions. This is a political decision about how fast we cut them. It's not a thing that fails. So I think the time order is emissions cuts first, but then if, and I'm not saying we know that it should happen, but if we ever do solar geoengineering, I think it wants to start relatively early for the reasons I said. And then really large-scale carbon removal actually starts after it. That says something profound about the need for a serious research effort. That says you might actually want to start this relatively soon. And we are nowhere near having enough scientific knowledge or having enough real debate about the public policy of this issue to make decisions about it. So let me come back a little bit to risks and then close and take questions. So at the beginning, I gave you this big, messy list of risks. And I think lots of different ways to divide these up. But I'm now keen on the idea of dividing them up into 4 categories. So these are my 4 categories. first of all, the physical risks of wise use. I've been trying to think of the right words. Actually, the first time I'm showing this slide. So what I mean by wise is utilitarian. That is according to one of these globally optimal models. This is the thing the IPCC and a bunch of other people who think about climate policy think about all the time. What is the utilitarian optimum? It's basically the answer from one of these Nordhaus-like models. Some of you may dispute whether that's wise, and in some ways I do too, but I think that's what I mean by wise, is when you're at least attempting to make everybody better off and nobody worse off, when that's your goal. So if that's wise use, then misuse is everything that's not wise use in this definition. And misuse means when maybe you're particularly trying to make you or your country better off and make some other country worse off. So that would be you're deliberately trying to bend the climate in a way that makes somebody worse off. Then there's this moral hazard question, and then a kind of big amorphous question about what it means to manipulate nature this way. So I'm happy to deal with these more in questions, but my view, maybe biased, is that the evidence so far about the direct physical risks of this kind of wise use are that they're real and that there's still lots we don't know about them. But to the extent that we do know about them, and for many of the risks now, there are several scientific papers that look at them, the risks look comparatively small compared to the benefits of wise use, from what we know now. But that still doesn't mean it makes sense to develop these technologies, because you develop a technology and you may hope it gets used widely, but it can be used other ways. And I haven't dealt with moral hazard. So let me deal, first of all, with the unwise use. I actually don't worry about that much, at least for aerosols in the stratosphere. And the reason is not the fact that I think everybody's good, but it's about the kind of underlying decisions that a country would really face. So there's no question that lots of countries and lots of individuals or interest groups want to make themselves better off and make others worse off. That's the reality. But if you think about this as a decision in the real world, there are, if you have two choices, maybe you're India, there's been a massive heat wave, and the government is seriously considering implementing solar geoengineering in some unilateral way. And sort of choice A is pure unilateralism, and you say you're just going to do it over the northern hemisphere, and maybe you know it's going to make China significantly worse off, but you're going to do it because it's the cheapest way, it protects you. That's choice A. And choice B is you actually maybe partner with some other countries, and you advocate doing it globally evenly in a way that hopefully makes nobody worse off. If you were really a lot better off under choice A, or if choice A saved you a lot of money, that would be tempting. But we don't have any evidence of that. It's so cheap to implement, the money isn't a big deal. And there isn't evidence you can make yourself a lot better off, say, by just doing one hemisphere. So my guess is that no country's an island. This is a world where the supposed one superpower gets less powerful every day, and where a lot of things end up being done collectively. Countries can't just do what they want. And in a situation like that, there are lots of different political issues at play. I think it's going to be unlikely that a country does this pure unilateral action, and more likely that a country finds a way to collaborate with some other countries in a coalition and aims for something that's closer to this global optimum, just because it makes it less likely there will be retaliation or other forces that try and stop them doing it. Still, in a way that's fundamentally self-interested, but self-interested taking into account what the likely actions of others are. So I think this is worth worrying about. I have worried about it. I write papers about it. But I think that, at least for the technology I talked about, it's maybe not such a deal. The big underlying concern is this concern about moral hazard. The concern that even inventing a technology like this, even talking about it, makes it easier or less easy to cut emissions. And there are, I think, two different aspects to it. One is individual behavioral. So if I give you some technology that reduces risk, in lots of cases, you will take on more risk. So that's true for wearing bicycle helmets and ski helmets, and you can demonstrate it with data. I think it's probably true for cars, for all sorts of things. Risk-reducing equipment tends to bring on more risky behavior. That's called risk compensation. There's nothing immoral about it. So I showed you pictures of these outdoor trips I've done. On that trip, we didn't have the batteries out, but we did have a sat phone. So if we got, somebody got into real trouble, we could put the battery back in and call for help. And I think that probably made us take more risk than if we hadn't had that sat phone. And I don't think there's anything immoral about that. Risk compensation is natural. Risk compensation around this at an individual level, though, isn't the issue. So first of all, there's some evidence that it goes the other way, which is really quite amazing. And second of all, the real issue is political, not individual choices. Let me tell you first the evidence that goes the other way. several different studies now, none done by us, have shown that if you take a group of regular citizens, one of them was a group of Germans, a woman called Christine Merck did, and you give the whole group some information about climate change, you give them all some money at the beginning, a certain number of euros, I don't remember how much. It's the way these psychology experiments are done. And you divide the group in half, and only one group one of the two gets told about solar geoengineering. And then at the end, you ask them how much of that money they want to give back to a carbon offsetting fund. So it's just a direct measure of how much they care. You ask them how much they care to cut emissions, but if they cut, they've got to give you some of the money they got back. And the big surprise was the group that got told about solar geoengineering was more motivated to cut emissions than the group that didn't. Exactly opposite to what you'd expect with this risk compensation model. And that's been replicated in several other experiments. Exactly what's going on isn't clear. It could be that simply talking about solar geoengineering makes climate change look more fearsome and real, reinforces the idea that experts really mean it. So essentially the logic is if experts are seriously contemplating something as wild as this, then the climate problem must really be bad. And that could explain that odd thing I showed you at the beginning, why it is that a kind of climate denialist website also doesn't like solar geoengineering, just like Naomi Klein doesn't like solar geoengineering. It's quite odd to think about, and that may be the underlying reaction. But the big issue about moral hazard is really political. It's the extent to which it would change the politics, the extent to which it would actually give more political power to forces that want to fight against emissions cuts. My view is you can argue it both ways. We simply don't know. But I don't think the arguments that it might do some of that are sufficiently strong to say the right answer is not to study this. That argument, I think, is a very high threshold that I cannot see meeting. I'm happy to take questions about the sort of bigger question of managing nature. And I think in closing, I want to say this. I mean, the central case I'm making is that research makes sense. And though I showed you some research results, it's important to say that there is essentially no research going on. I mean, so $10 million out of a global budget that's close to $10 billion on climate science, it amounts to close to nothing. And I don't think people make good decisions when there are taboos. Whether something is good or bad, getting it out in the open and studying it is, I think, the right thing to do. And I think the big lesson is neither I nor most people in this room, not my generation, I'm 56, we are not going to make the decisions about whether or not this technology gets used. That decision gets made by the next generation. The decision we can make now is about whether we have a really serious research program. So sometime in the next decades, whether or not we have a research program, I think it's likely some national government is going to get to the point of taking this very seriously. I actually don't think it's likely to be one of the biggest governments, the US or China, right away. It's more likely to be a smaller and less stable government that has some really big climate impact and decides to take it seriously. That's not a statement that's a good or bad, it's a statement that I think is likely. And that will push this on the international agenda and the decisions will have to get made. And my view is that the long period that we've had of trying to pretend that the right way to handle this technology was just to pretend it wasn't there and hope it went away, that's unhealthy. And what we need is a really substantial research effort, one that has a scale of more like 10% or 5% of the total amount of funds we spend on climate science, and that's sort of integrated in, and one that really has many groups whose job it is to figure out all the ways that folks like me are wrong, to try and really understand what the problems are, kind of it's not the right word maybe for climate, but a red team, blue team approach, where we have some groups trying to figure out how these technologies might be developed and used, and other groups trying to figure out the different ways they go wrong. I think that's the way you develop some confidence that things are understood. I think it should be a non-commercial effort, because capitalism is great at making things cheaper, but this isn't about cheaper. It's so cheap we don't need to make it cheaper. It's about developing more shared trust that we understand the risks and that we can monitor and that we know what different countries are doing. So I think this is something that should be principally done by researchers, universities, by NGOs, by governments in a way that is as transparent as it can be in this divided world. So what I'm advocating for is a really serious research program. And what I'm advocating against is what happened for too long on the last topic on my list of my chain of 4, which is adaptation. So I'll close there. 15 years ago, adaptation was in many ways in climate circles had almost as negative a connotation as solar geoengineering does now. So people like Al Gore used to call it the A word. We weren't supposed to talk about it. And the reason was that if we started to work with communities and tell them how to protect themselves from climate change, that would somehow make them think that it was all okay and that we didn't need to cut emissions. And so the idea was we just shouldn't talk about it. And I think that was, I think it was bad policy. I also think it's immoral. And that's changed. Now, almost all major governments have serious programs, and not just major governments, but down to our city here in Cambridge, have programs that are now often called climate resilience, but it's what we used to call climate adaptation, trying to understand how we can reduce our climate risk, which I think is the right thing to do. And I don't think it's meant that we've done less to cut emissions. So I'd like to close it there, and I'd love to get comments, especially I'd love to get real criticism, because I think this is a hard social choice about how we talk about and develop technologies like this. And I know lots of technical details, but I don't have any more vote or any more moral authority than anybody else in this room, and I want to hear your opinions. Thank you.